You have to trust me. He's somewhere here. And he's not so famous, but he's famous also. Gregoire, he should be somewhere, I don't know where, here, you know. They took this picture. And this, in fact, are ancient channels through which meltons flow to the mantle, okay? This is from Mike Brown. You can see, you have concentration of melt. So it's not a dike, because the dike is full of melt, crystallizing after, but it just, because they start to concentrate and to move like this. Well, this is not very important, it's in detail. Dikes. Our dikes is cross-cutting mantle peridotite. You know, here you have dikes of pyroxenite. It's only pyroxenite. You don't have pervasive flow. In the Trinity of Phyolite in California, you know the size. You have the hammer here. It's a few centimeters, the size. Here another in Great Britain, the Lizard of Phyolite. Lizard of Phyolite is south of England. You have some dikes here. You have one like this and like this, like that. It's a troctolite. So troctolite is olivine and plagioclase mostly. Another example in the island, Bay of Island of Phyolite, still in US, but in the eastern part, in the northern Appalachian, you know, you have this kind of dikes of orthopyroxenite. It's more than 90% of orthopyroxene going through an arsborgite. So if we come back to monophyolite, well, of course, there is plenty of study about monophyolite, but I will focus and I will reduce to the evidence and the two main type of dikes and flow we have in the mantle from the monophyolite. In Oman, the porous flow structure is filled by mostly troctolite. So it's a gabbro, but you replace the clinopyroxene by olivine. Okay, so it's plagioclase olivine. So you have this one, we already shown. You have this one, you know, everything is troctolite and they're moving within the mantle. You know, there is a lot of this structure all around the phyolite. Sometimes this horizon, because it's not dikes, you know, when they concentrate a little bit, they are parallel to the submoe. You know, the moe is here. You have the crustal part of the phyolite, you have the mantle part. And if you have some horizon of troctolite, they are parallel to this paleo-moe. So a guy we know, Mathieu Benoit, one time he said, these troctolite are the purest accumulate I ever seen. So you imagine, pure accumulates. You know, they look very fresh, very nice, and it's only nice olivine, nice plagioclase. So it's a evidence of the famous cotectic olivine plagioclase of the morb. You crystallize together olivine and plagioclase at some a pressure around 2 kilobar. You know, it's here. You have this is this point here occurring in this experiment. You know, MgO content. Here is the percentage of crystallization, the temperature. You are here, in fact, when you have a rock like this. If you estimate your pressure at around 2 kilobar, you are exactly here. And you form plagioclase and olivine at the same time, so you are close to 1210 degrees. Okay? 1,200 and for the experiment here it was 14, but it's close, you know, it's between 1,200 and 1,250. Okay? So you have evidence, just with your microscope, just on the field, you see the evidence of this cotectic in the case of Oman. The dikes at the opposite, the second main structure, they are filled with olivine gabbro. Olivine gabbro is made of olivine, plagioclase, clinopyroxene, and in this case, the evidence, this point in this diagram, still the same, magnesium, percentage of crystallization and temperature, and we are here, sorry, it's around, my eye is not so good, 11 something, 1180. So you have a quantitative estimation of the temperature of crystallization of this assemblage. You know, the rocks are very, 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 very fresh. They occur also in a lot of places in the monophyolite. They cross-cut the peridotite. So pervasive is with troctolite and for the morb, and for the dikes is filled with olivine-bearing gabbro. Sometimes we have a second type of morb dikes with morb affinity, dikes with crystallization on the inner wall here, frequently sheared. You know, you have some movement like this, and we are filled with orthopyroxene, with or without hornblende, amphibole, with in fact, they are oxide-bearing gabbro. And in fact, it's just an evidence of fractionation of morb. They are more differentiated, you know. They are no, less primitive than the olivine gabbro and the troctolite we saw before. It's a very nice kind of rocks. It's very nice monophyolite because it's almost a desert, so you have all the rocks at your disposition. Sometimes it's very, very complicated, but you know, the rocks, they look good. So a monophyolite allows the determination of the temperature of the transition between the brittle and the ductile. I will show you. Transition from morb migration into the shallow mantle, because the mantle section of a phyolite are always shallower portion of the mantle. Why? Look, I come back to the two main kind of rocks we have. We have reactive porous flow channel, remember, and we have dikes. Fracture is the same. So here, if we are, you know, we are just at the transition between these two kind of circulation. So these are filled with troctolite. These dikes are filled with olivine-bearing gabbro. So, you know, we may estimate that the transition between that point, olivine plagioclase, giving troctolite, and this area here, you know, we are between, let's say, 1200 and 1190 degrees, or a little bit less. So you have an estimate of the temperature of the transition between the porous flow and the formation of dikes, you know, just because you have this assemblage, cotectic assemblage, okay? But the morb product in the monophyolite are not alone within the mantle section of the phyolite. We are still focusing on mantle section. Indeed, we have also kind of rocks forming dikes. Not only olivine gabbro, we have also pyroxenite. Look at this one. It's a very nice one. We have pegmatite of gabronorite. Our gabronorite is plagioclase orthopyroxene. Okay? Gabbro is plagioclase clinopyroxene. Troctolite is olivine plagioclase, and the gabronorite is orthopyroxene plagioclase. Okay? So you have an example here, pegmatite with the big plagioclase and the big orthopyroxene. One example here. So this occurs also in the mantle. And this second suite of rocks, we show we are looking at the morb suite. So this new one with pyroxenite and gabronorite derived from melt higher in silica content and water if you compare to morb. And they are very depleted in incompatible elements if you compare to morb. Dikes belonging to this, what we call depleted suite, are the most common in Oman-Harzburgite, more common than the morb suite. Their structural and textural characteristics show that they crystallize probably from a mantle colder than the melt, of course, likely in the range 600 to 1100 degrees. A possible origin for the parental melt of this suite is in situ partial melting of the shallow and partly hydrated lithosphere residue after the morb extraction, as proposed by the famous scientist Michel Gregoire in 1999. He was not. I told him that I will talk about him, but not this. So just the model they proposed in, you know, it was a famous paper, look at Nature. So hypothesis, I finish. Hypothesis hydrated melting of the depleted lithosphere at oceanic spreading center due to episodic character of mantle diaparism. So you have the morb step, you know, you have your diapir coming here. You form the morb, like in a lot of Middle-Sine ridge. So after that, you stop the magmatic production of morb. So, and you put some water from the sea by hydrothermalism, and they are going by fracture down to the upper part of the upper mantle here, and they put water, and now you know the free possibility to melt the mantle. You increase the temperature, decrease the pressure, or you add volatile, in this case water in the mantle, so your mantle will melt, but you will melt the upper part and this upper part is already a residue after the partial melting giving you the MURB. So this is why they are very depleted into this element, and you have the characteristic of the dikes I show you, the norite, the gabronorite, and the pyroxenite. And after that, you go again to a new diapir coming in, and you form MURB, and after you form, This is why you have two suites. The normal MURB, and after you stop this production of normal MURB, you put water in your residue, mantle residue, and you form what we call the depleted suite. So one of the questions was among these two magma series we have as pervasive structure or dikes into the mantle, which one is feeding the crust? It's very important because the mantle, you see, is just small dikes, and after you have a crust. But in fact, if you look simple electron microprobe data, and titanium in, I think it's in clinopyroxene, the XMG, the number of clinopyroxene also, and here it's anorthite in plagioclase against the MG number of clinopyroxene. All the cumulates from the crust in a man display intermediate composition between those of the magmatic series I showed you before in the mantle, so MURB and depleted. Therefore, one of the main new conclusions, I give you the reference here. Therefore, parental magma of the layered cumulate are hybrid magma between the MURB and the depleted. You have two end members, but all your melt coming to the crust are product of the mixing between these two end members. So sometimes you have just a little bit of MURB inside the depleted one, or just a little bit of depleted one into the MURB. This is why you have almost pure MURB in some part and pure depleted one in some part. So, let's remember, the biggest ophiolite in the world is made of two main magmatic series. Not only the MURB one, everybody knows, but also this depleted one. So we are moving to the nice country of Donald Trump. So, but not to look after Donald, we look after the trinity of ophiolite. To show what I like to study, I know you know my major concern in mantle is metasomatism, reaction between melt and rocks, and like this kind of stuff, because you can measure with the laser and so on. Melt reaction rocks leading to depletion. I will come back to the things I showed you very quickly last week about this kind of depletion by melt-mantle reaction. So just to remember you, the two ophiolites are very different. In what we call the somile is another name for the Oman ophiolite. The production of melt was very high. It's a place with high melting degree. So you have a big, thick crust, the typical one with the cumulates at the base of the crust, massive gabbro, sheeted dikes, and pillow lavas, and the mantle section with the two kind of dikes. But if you compare to Trinity is much thinner, especially the crust here. And you have at most the same size for the mantle section, but the crust is very thin. You have only diabase, and after you go back to pillow lava, but everything is thinner because on the wall, on average, the melting degrees was much, much lower. So George and his wife were working on this ophiolite. So they concentrate in a very nice section, the Bear Creek ophiolite. Bear Creek, you understand why. Sometimes I think they met once or twice bears. Not the very big one, not the grizzly, but the brown one. But even with the brown one, you stay a little bit away. It's like yesterday when you tell me that you have some tiger around. I was not looking very bad. So let's go back to Bear Creek section. They do the stratigraphy. So you are going from the base of a typical crustal section with layered pyroxenite and dunite, and you go up to the crustal section. But in detail, what they find in this creek is kind of a magma chamber, occurring within the periodic depleted mantle section here. It's made of gabbroic segregation. Here you have the photo here. You have the layered cumulate with pyroxenite. You have some mantle enclave here with cumulates. They come from the wall rock. They are inside here. You have gabbros at the top, diabase, the upper part. You have the peridotic mantle with some vein also, you know, pyroxenitic vein, gabbroic vein occurring within the mantle. It's a very nice detailed study because it's, you know, on the field you have a large outcrop, large occurrences, so you can go to very good detailed study, especially if your ophiolite are not very altered. This is the good quality of ophiolite compared to xenolith. I remember xenolith are of small size commonly, very fresh, but difficult to have the big relationship. Here, you can see everything, so you can draw this kind of interpretation at what you see. And remember, it's only one interpretation, it's a good one. But it's bad. You have to do a very good interpretation, you have to stay for a long time on the field and be very precise, and this is the base of everything. For the xenolith, it's not the same. You take your oil to go back, and you do chemistry as a top. But for ophiolite, you are very careful because everything you will do after depends on the quality of your work on the field. So the evidence that the Trinity magma chambers, like the one I just showed you, are intrusion of huge melt batches in a relatively cold lithospheric mantle. Quite differentiation if it's melt by fractional crystallization, development of a clear magmatic stratigraphy within the intrusion. It's clearly evidenced here, you know, the stratigraphy of this. And the crystallization sequence, the study of the characteristic of the mineral and the rocks we have evoke a parental melt such as a boninitic, we have already this discussion, poor in aluminium. One of the ways to focus on the boninitic nature is here is evidenced by the mineral chemistry, Trinity ophiolite. You have the titanium in clinopyroxene, the HMG number in clinopyroxene. They report the composition of the Trinity cumulates, you know, the base of the, of the crystal section. Clinopyroxene from the lersolite, from the mantle lersolite. I forgot to tell you, it's mostly lersolite, the periodic, because the degree of melting was low. We don't have too much arsborgite. I remember, more we melt the mantle, more we go from lersolite to arsborgite. So it's mostly lersolite, and with plagioclase and spinel, because we are in the transition between the spinel stability field and the plagioclase stability field. So clinopyroxene from lersolite, clinopyroxene for the Trinity cumulate, the database for clinopyroxene from boninite, and here a database from clinopyroxene from morb, and you can see that everything is closer to this kind of clinopyroxene, especially for the cumulates. See, and cumulates are linked to the dikes we show also in the mantle. So to go back to the mantle section, we perform a detailed petrological study of some vein linked to these cumulates occurring in the crust, cross-coating the peridotite lersolite from the ophiolite. So I already show you this. It's a little bit more clear here because I put some line. You know, you have a vepicerate vein going through a spinel arsborgite, and far from the vein you have spinel and plagioclase arsborgite in this case. Sometimes you have also lersolite, but it's far from the vein. That means that when you form this vein, you probably have some melt going through the peridotite, reacting with the plagioclase. This is why you have no more plagioclase within this part. It's a optical evidence, simple optical evidence that you have a reaction between a melt here going and giving the vein and the surrounding spinel plagioclase peridotite. So we did the modal composition by point counting. You see here it's a clinopyroxene and orthopyroxene. Here, the vein, the whole rock of the vein with spinel arsborgite without plagioclase, and far you have the typical spinel and plagioclase peridotite from Trinity. So that means that the melt probably percolate from your vein, not too far, and was reacting. This is why we think it was probably low in aluminium. As is low in aluminium, you know that plagioclase is high in aluminium. So they don't like each other, so they react, and you dissolve your plagioclase, and in fact you form a spinel arsborgite. And when you go further, probably here we see the optical evidence we stop the percolation of melt, at least the percolation giving this reaction, and after you go to the normal surrounding rocks, spinel and plagioclase lasolite. No, in this case, it's probably a modal evidence because you change the mineralogy. But in fact, if you go in detail, you know between the modal percolation and the cryptic percolation, you have a little bit of cryptic percolation here because you still have some change in chemical composition few centimeters after the limit. So, but in this case, yes, you change the mineralogy. So, but people working on ophiolite, they don't use too much cryptic and modal. But yes, it's the same. So the modal estimation, you know, Webster-Wright in the middle, plagioclase is stopping, you know. Yes, it's a detail. We have some, you know, chrome spinel also, but not in the vein. We never find, you know, the vein is without spinel. So laser. So the good thing with laser, you work at a diameter of less than 50 microns. So what we did is thick section, you know, in this cross section, we did a lot of thick section from ear to ear. I mean thick section because you can't use the thin section you have the use to use under your microscope because the laser is going through too quickly. So we need 100 micrometer thick section to work. So we did like this, and so the nice picture for the titanium in clinopyroxene, we focus on clinopyroxene. We were surprised because we have a depletion in titanium from the vein to the surrounding. I will show you more. Yttrium going the same way. You see, from the part where plagioclase disappear, you continue to increase your yttrium, and after you have the plateau. Probably you continue to react here, but it's just a cryptic, it's just a chemical change here, in this part. Here you have the modal change. The same for samarium, you know. Samarium is the same. You continue to increase here, and you have this plateau. Holmium, here terbium. So it's working for a light rare earth element, heavy rare earth element. And zirconium, and the HFSC also, they are working. So this kind of vein is very depleted. The Websterite is very depleted if you compare to the lasolite. For the strontium, you have the opposite. It's normal because you are focusing on clinopyroxene, not on wall rock. If the plagioclase disappear, you have to put the strontium somewhere. So the only mineral they remain inside your rocks are orthopyroxene, olivine, spinel, and clinopyroxene. And the higher partition coefficient between all these phases is for the clinopyroxene. So the strontium is going to the clinopyroxene. Okay, if this is just the evidence where we have the disappearance of plagioclase in the wall rock. So, of course, as I told you last week, when you have only one sample, you have to be sure that your sample is representative of your ophiolite. So what we did after, we did rare earth element study in this case it was for the wall rock. We have thick dikes enough to be able to cut the rocks to have the center part of your rock and to do wall rock. And you find the same way, you know, for the pyroxenitic vein, it's a Websterite, clinopyroxenite. They are lower in rare earth element. It's working a lot also for a lot of incompatible to S element. They are lower in concentration if you compare to the periodic wall rock with a typical negative European anomaly because you have plagioclase. No, if you have plagioclase, it's a positive one. No, it's an evidence of partial melting. Sorry. But you know, yes, I'm coming back to this one. You know, even the peridotite, they are not very enriched rocks. Because if you look at the light rare earth element, they are very depleted. So you have the evidence that these lasolites were previously molten. They are residue of melting, probably around between 5 and 10%. But even these residue are higher in rare earth element if you compare to our magmatic vein going through them. So you have to think about a very depleted melt. But you know, and this vein come from all over the ophiolite. So we are sure that my sample was representative of the story of the ophiolite. So we go back like this. This one is on clinopyroxene. We have the same anomaly, you know, for the lersolite. Plagioclase bearing lersolite cumulates for the clinopyroxene, the same feature than for the wall rock. So you can also conclude that your clinopyroxene is explaining you the concentration of your rocks, because you have the same feature. And we know that is true because we don't have other phases than 2-pyroxene, olivine, and spinel. So the main concentration of incompatible twice elements are going to the clinopyroxene. It's not the same if you add amphibole and other minerals. But within a typical peridotite made of these 4 main phases, this is why we focus a lot with the laser on clinopyroxene, because there is a main reservoir of incompatible twice elements. So now we are moving a little bit to orthopyroxene, because the problem with clinopyroxene, it always occurs in few percent. I don't know a lersolite, a typical mantle lersolite with more than 15, let's say 15, 70% of clinopyroxene. So now we are to start with the orthopyroxene, but this is another story. Pyroxene vein, you know, the cumulate are very depleted, the vein a little bit less, probably because you have a little bit of remaining melt component within the vein, but still very depleted if compared to plagioclase lersolite. We have also, I didn't show you, but yes, I show you, you remember the gabbroic segregate at the top of the chamber. They are very different. You know, they have a rare of element more similar to the one of plagioclase lersolite. They are typically morb segregates, coming probably from the partial melting of the lersolite. So the melt that flow in the reactive websterite vein are issued from the same depleted source than the melt that fed the magma chamber. And similar conclusion than in a man. We have the same, at least very similar feature between the vein cross-cutting the mantle section and the cumulate from the lower part of the crust. So we can conclude this. Some people, they estimate the age. You know, it was from 45 to 405 and 440 million years ago. Of course, they didn't estimate with this kind of rocks. They estimate with more differentiated rocks, like plagiogranite with some zircon inside and this kind of stuff, is this age. And the gabbroic segregation here are issued from low melting degree of the plagioclase lersolite, as I told you, and around 470 million years ago. So the big question is also, is the chemical effect of melt peridotite evidenced by the study of the websteritic vein, I show you, responsible of the geochemical variability of the Trinity mantle peridotite as a whole? Just, you know, here I report in a still the same, titanium in clinopyroxene, it's from Collener and Lossuer, XMG number in clinopyroxene. You know, you have the dikes, the Trinity peridotite. And in fact, if you report all the wall rock here, you know, the dike wall, you have a range in composition from the typical Trinity peridotite far from the dikes to the very dikes. So you can see here, the answer is yes, because we change, even at the scale of the major element composition of clinopyroxene, we change the composition of the peridotite from the Trinity, just because we put dike inside, you know, and you have this peridotite dike walls, is peridotite also, you know, with this kind of composition. So range in periodic composition at the scale of the massif, an effect of melt rock reaction, yes, because we have this big range. You know, the range in periodic composition at the scale of the massif, also here, we put titanium in spinel against chromium in spinel. So it works also for the spinel. So the mantle plagioclase peridotite, for the websterite, from the vein, mantle peridotite dike wall, here, the cumulates, you know, so percolation of the melt giving the cumulates within the crust change the composition of your perioditic mantle, you know, so you are working at the scale of the massif. Rock reaction can lead to defertilization. Remember that we have very depleted melt giving the websterite. So in this case, it's not the typical world from Bodinier, you know, people working on orogenic periodicity massive, they are talking about refertilization of the mantle by melt, refertilization process by circulation of melt within the mantle. In fact, a peridotite is a palimpsest. Its composition reflects the composition of the last melt that percolated through it. It's very important. Much of the cases, if you are lucky, remember the xenolith, sometimes we have some evidence that you have previous melting degree. But in a lot of samples, you can't see anymore what happened before. Because you have so large volume of melt coming into your mantle, that change the composition, and in fact, your mantle peridotite is giving you the last history she underwent. So mineral composition, can it be used alone to estimate the degree of decompression melting in suffered? You know, it's a composition for people working on oceanic rigid and ophiolite. The importance of the melt reaction process within the mantle section of ophiolite. Thank you. If you have questions. A very important thing to remember is that the MORB melt are not alone in ophiolite, and probably in the oceanic ridges. No, typically, when you are not a specialist of ophiolite, as I was before I start to interact with Mathieu and Georges. So ophiolite is like mid-oceanic ridges. We have a lot of MORB everywhere, but in fact, you know, in Trinity, in Oman, in other ophiolite, we have evidence where we have a completely different melt. In this case, I forgot to tell you, it's maybe not linked with the same model than Mathieu proposed for Oman, you know, circulation of fluid going to remelt your Harzburgite. It's a supra-subduction zone, Trinity. So these boninites are probably linked to subduction. But in fact, that also evidence you that, you know, depleted melt can also come from different settings. No, this is not because you have a depleted melt in Oman. Here you have to think straight to subduction. Okay, you have to test this. You have to be sure. This is a difficulty sometimes to interpret your data. You have 2 or 3 hypotheses, and you have to be sure that the one you are giving to people by publication are the best one and the most constrained one. Between? When you have a dikes, your dikes is cross-cutting your peridotite and filling the dikes in only the magmatic product. For the flow, even if you have, they look like dikes sometimes, if you look in detail, you still have your peridotite, and you have just evidence of the melt going around the grain. It's white on the picture. Why? Because it's made of plagioclase now. So in fact, but a dikes is filled with a completely different rocks from the peridotite. Commonly, spiroxenite, gabbro. The channel, the flow channel, is a peridotite, but at the grain boundary, you have evidence of circulation of melt. So it's very easy to recognize under the microscope. You have mostly a plagioclase bearing peridotite within your channel, and peridotite, normal peridotite, and the wall rock. For the dikes, you have a gabbro inside the dikes, and the surrounding rocks is a peridotite. Because it's not the same process. For the flow, you are going, you know, the melt is interconnected, it's going in between the peridotic grain. Dikes, you need to have brittle peridotite, you have pressure, the melt is coming up, you have pressure, you break up your peridotite, and the melt is coming inside, okay? More questions? But I think the margin are not shield in Oman. No? Because the temperature is too high. You know, to have shield margin, you need to have a very large difference of temperature between your wall rock and your dikes. Here we are working in the mantle. But even if I tell you that the mantle is a little bit cold, it's still at 700, 800 degrees. You know, to do a typical shield margin like we can see in the crust, for example, when you put dikes inside sedimentary rocks. Sedimentary is very low in temperature. Your dike is a magma, so you can see the shield margin. But in this case, it's difficult. You see, with Trinity, we see the change in pleasure class disappear, but after you continue the reaction, because you have also high temperature, so the reaction can continue to occur. It's difficult because if you add to this complexity, for example, you will know people working on the actual crust, actual ridges. We have different kind of ridges. If you have low velocity, if you have a low production of melt, you don't have the same structure. So after to go back to ophiolite, even in this one, they are very fresh. We don't have problem of crustal metamorphism, big alteration giving serpentinite. Even like this, it's difficult to directly link ophiolite, young ophiolite like this, well, not the Trinity, it's not young, but ophiolite like this to the mid-ocean ridges, the oceanic crust is not obvious. So the only way, I think, probably to solve this is what George and co-workers did is a lot of sample, lot of study, lot of data from the human ophiolite, and after a while you start to understand. This is pretty new. The idea to have that the melt forming the crust are not typically moored, not typical depleted melt. They are the mixing between the two. It's a very new result, so we have to think about this. So this is also to tell you that when you go back to what we can alpine ophiolite occurring in mountain, with a big history of metamorphism, of alteration, of everything, it's very difficult to work, to deal with this kind of ophiolite. And especially if your mantle section is serpentinized, sometimes you have only chromite. So the idea is we don't have to surinterpret our data. If we can go too far, we stop. I mean, if we have only one mineral, we use this mineral, we give the information this mineral can tell us, and after we stop. We stop. If we can do further, it's better to stop than to do some stupidity after, given bad data and bad interpretation. And of course, it's frustrating. In some part, even in the Alps, in the French part of the Alps, you find some old remnant of ophiolite. You go to the field, it's a nightmare. Even the gabbro, even the crystal section is just serpentinized, it's just transformed to something else. So if you like to, it's good for people focusing on alteration process, formation of mountain, for people looking at what were this ophiolite before, you stop. Central massif, people, it's very good because we know that the Variscan chain was a very large one, probably similar to the Alps and Himalaya now. And you go to the field in the central part of France, you find some, peridotite. And if you are lucky, sometimes you find a remnant of orthopyroxene. Or if you find a remnant of cyanopyroxene or orthopyroxene, you can work a little bit. But most of the ophiolite is just altered. So it's a nice place. That's it. More question before we go to isotopes? Thanks. Mathieu, you bring your own. Thank you. Alors, si tu veux, j'ai trouvé le moyen de changer les diapos avec le... Non. J'ai trouvé qu'il y avait ça dedans. Tu diras à personne, j'ai trouvé au bout de... Ah non. Ça va sortir, ça va rentrer. Ça marche. Ouais, c'est bon, tu peux l'arrêter. Ouais.
Okay, this is my last lecture about general notion of isotope geochemistry. The lecture after this one will be a case study mainly what did some PhD student who worked with me. Of course. Some PhD students, so I have 3 case studies. I hope to have the time to do the 3 case studies. One will be about continental volcanism. Second will be about subduction volcanism. And the third one will be about ridge setting, oceanic ridge setting volcanism. Not far from you, in fact, in the Indian ridge. So this last lecture is about continental crust, subcontinental lithospheric mantle. An overview, really, because it's very, very complicated, very complex, and it was not at all, for long, the playground of geochemists. You know, geochemists, petrologists, and even geophysicists were basically most of the time working on the oceanic crust and the mantle. It was the playground of geochemists to speak about the whole Earth and the mantle, etc. The crust was the playground of tectonicians. Simply because you have only access to the surface, especially through the volcanism. It's difficult to have access to the deep crust. And so the vast majority of isotopic data you have on the continental crust are datings, ages, okay? The part of geochemistry which is mainly used for continental study are radiogenic ages, okay? Especially zircons. And until now, the vast majority of paper you can find on continental crust are paper who are dating because the tectonician needs ages to tell about the story, about the construction of the continental crust. Okay, so I will start with some example and the idea about what we know about the mantle, the lithospheric mantle under the continental crust. Then I will rise up. We will discuss about the lower crust and then the upper crust, and you will see that most of what I'm going to say is model related because we have very little access on this sample. So let's start with some remind about differentiation. Okay, you remember this diagram? This is a trace element average pattern of what we believe to be the continental crust here, the residual mantle, and of course, if you are, like Michel was telling you before, if you are stacking and freezing some lithospheric mantle under the craton, it should be residual, okay? Otherwise, it will go down again into convection. So if it is residual, it should have a depleted trace elements pattern. And if you are isolating this subcontinental lithospheric mantle for a long time, like for the depleted mantle, you should develop a specific isotopic signature. So typically, if you come back to this diagram here, continental crust is there. You should have, for example, in neodymium, very radiogenic, it is neodymium, unradiogenic isotopic signature, and normally you should have radiogenic, very radiogenic, if it's very old. If it's Archean, you should have very, very radiogenic isotopic signature in the mantle, especially because it's isolated comparatively to the convective mantle when you can refertilize it by subduction, introducing subduction products within, etc. But normally, if it's old and stable and untouched, you should have very primitive, what we call primitive, or depleted. There are different ways to use it. Primitive, depleted, radiogenic composition. Okay? So, now, what we can see. So, this first diagram here is neodymium, strontium, age-corrected isotopic composition of the continental volcanism. So why continental volcanism? Because there are some hypotheses that part of the continental volcanism is originating into the subcontinental mantle lithosphere. You will see that it's maybe not true, but it was one of the hypotheses. If you see the spreading, so you have different fields, okay, that's the way the geochemists, you know that, love to represent their data. Potatoes, okay. Potatoes are very useful, because when you have a large random plotting of your sample in a diagram without any trend, you have nothing to say, just random, and if you draw a potato around, then you have a mantle domain. Never forget about this. Potatoes are very useful. This is a way to interpret your data. So you have plenty of potatoes, and globally, you see, they are still fitting a sort of negative correlation between strontium and neodymium, fortunately. So there is the same logic, okay? But very large spreading. You go to 702 to 722 here on the strontium, and for neodymium, you go to 513 to 5125 here. So a large spreading. And if you compare this to the mantle sort of compilation of xenolite, and so here you have the spinel xenolite and here the garnet xenolite, you see that they are still, fortunately, showing this kind of relation, but some of them are depleted, but most of them are not. And also, they are not spreading as the continental volcanism is spreading. So there is a problem. If the continental volcanism is originating from the subcontinental mantle lithosphere, we should find the same spreading. We should find the same. If this is the source of this, we should find the same isotopic composition as, you know, the partial melting is not fractionating the isotope. This is not the case. So there is some option for that. Either they are not related. Okay, continental volcanism is going from somewhere else, or these have been changed through time, and then you can think about what Michel told you about the Archean subcontinental mantle, Proterozoic subcontinental mantle, and all these different refertilization of the mantle, which can change the isotopic composition, or this magmatism have been changed by a secondary process. So the first secondary process is something we can get rid of, is alteration, surface weathering, etc. But we are able on the field to sample some fresh lavas. And the second, which is not really a secondary process, which is a primary process, but still changing the composition, is crustal contamination. And typically upper crust or lower crust crustal contamination. And the third hypothesis, so if they are not related, so if they are not related and there is no crustal contamination, then the source is not the subcontinental lithospheric mantle, it's something under, like a plume, mantle plume, for example. So a second problem with this composition here is we believed, maybe Michel will say the opposite, but for geochemists, we believe that normally the garnet lertholite in the subcontinental lithospheric mantle should be older than the spinel one in terms of stabilization of the mantle. And the problem, if it's older and it has been not changed during time, it should be there. The black dots should be there, because if they are older and untouched, they should have very, very, very depleted isotopic composition, and the spinel one should be there because they are more recent stabilization of mantle in the mantle. And we saw the opposite. So the only way to find the opposite in this kind of diagram is mantle metasomatism. And this is the main problem we have, and Michel also speak about it, about the trace elements. We have the same problem for isotopes. Most of the sample, which are brought back to us by the volcanism, have experienced melt metasomatism. And melt metasomatism, you saw the effect on the trace elements, but also it has an effect on the isotopes. It is resetting the isotopic system, because if you think about it, mantle metasomatism is just the opposite to partial melting. Partial melting, you are homogenizing the isotopic composition of your source rock and you are putting it into the melt. This is the basic hypothesis we have, that the melt are in equilibrium with the source when we deal with oceanic setting magmatism. But the opposite is true. If you introduce a melt in the peridotitic matrix, then you will reset all the minerals clock in terms of isotopes, and then you will have at the end an isotopic composition which is an average between the isotopic composition which was before in your subcontinental lithospheric mantle and the isotopic composition of the melt. And this is the main issue when we deal with isotopic ratio in lithospheric mantle. Most of the time, most of the sample you are measured, except for very rare system, for the normal radiogenic system like uranium lead, lutetium hafnium, samarium neodymium, and rubidium strontium, they have been reset by the last melt event. They suffer. Okay. So, what can we say about this mantle if everything is reset in terms of isotopes? Normally nothing. Okay, we just can tell something about the last melting episode. So maybe we can use some other type of xenoliths. The crystal one, fitting the arc volcanism, a trace elements pattern. So means the E-type granites have roughly, in average, the same composition as the magmatism in arc. So they should be related somewhere to the arc magmatism. But despite of this, the people, and most of there are big school of thought in the world, people propose that they have nothing to do. There is no crystal growth, and there are no direct relation. They are not, in fact, the crystallization products, or they are not related to the arc magmatism directly, and there is no crystal growth. And they develop this kind of theory. This is the people in South Africa, for example, all the people from Clements and Stevens. They developed this approach, just plotting the isotopic ratio, the compilation of isotopic ratio against a fractionation index. Here this is iron plus magnesium in granite. And they developed this approach telling that there is no logic in terms of isotopics change as a function of the fractionation index. And then if there is no change, then there is no relation between the isotopic composition and the arc magma and the generation of continental crust. So it's a little bit tricky to understand, because they developed this kind of approach to vanish, and this is the topic of my next slide, to vanish the hypothesis that in fact E-type granites are the product of interaction of the arc magma and the continental crust. through process like assimilation fractional crystallization. Because you cannot imagine that you are putting a large volume of new magmatic material in the crust without interaction with the crust which was there before. And the other hypothesis, the other major hypothesis against the work of Clements and Stevens, this is the hypothesis where the arc magma are coming inside the crust and they are interacting a lot in terms of magma melt rock reaction with the continental crust. So they are contaminated by the continental crust through process like assimilation, fractional crystallization. And if you remember the equation I told you about AFC, this assimilation fractional crystallization process, this is simultaneous digestion of the crust and crystallization. Okay, so you should have a link between the change into the isotopic composition and the fractionation index. If you are assimilating a crustal material, then you are changing your isotopic composition, and so you should have a trend between the fractional crystallization index and the isotopic composition. And Clements and Stevens use this kind of diagram to say, no, this is not the case. So the second hypothesis is assimilation fractional crystallization. So you remember, melt is coming, it's fractionating, assimilating, and then you can compute the evolution of this with using the AFC equation. And I show you here an example we did with during the Sophie Demouy PhD thesis. We had a lot of E-type granite from Peru, and it will be a topic of one of my presentation, but this slide will not be in the presentation. And we try to compute the AFC, and we end with the same result as the Clements team. There is some problem to explain directly in granite the isotopic composition, the change in isotopic composition with a process like AFC, because there is no clear link between the isotopic composition and the fractionation index. So it's physically possible, but rarely supported by the data. So are Clements true? Are we producing the continental crust only in a closed system? And we are not, in fact, we are not producing continental crust. We are just changing the nature. We are rejuvenating the continental crust. We have some arc magma going to the surface, but the majority of the continent is a stable system and closed system. And the main hypothesis of the Clements hypothesis is the occurrence of perithetic minerals in the granite. They say we have this is not a fractional crystallization product. This is not really a melt. I speak about the granite. This is not a melt. This is not a fractional crystallization rock. This is not accumulate. Okay, this is not accumulate. This is a melt. This is between both. And in fact, the occurrence of perithetic minerals are minerals which are transported in the granitic melt from the source to the surface. And then, because of the occurrence of these perithetic minerals and the occurrence of inherited zircon core in the granite, which have some trace of the lower crust, then this is the lower crust which is melting. Okay, so then we end with the question, is this process occurring? Are we creating continental crust? And then is what the process, the way it is, if it is the way, is it the way we were creating the continental crust in the past? Or in fact, this is another process, and the continental crust is not subduction related. Okay, the majority of the continental crust. Now what we see is rejuvenation of the continental crust, but we are not creating continental crust. So when we deal with old continental crust, there is another point which is difficult to assess, is that you need to do edge correction on your signal. And I told you it's very easy to change the isotopic composition. So then we end with a patchwork of a large variety of magmatic events. And in fact, you will see maybe tomorrow in the case study I'm going to present that it's difficult to give them a global model for the generation of the continental crust. Mainly, sometimes you have to deal with a local magmatic system and try to explain for this magmatic system what happened, and not try to deal with all the E-type granite in the world and explain that, say that continental crust is not growing and it's not directly subduction related, okay, and it's remelting or it's subduction related through this process. You have to deal with your own magmatic theory in a local place and then explain what happened in your magmatic system, and then you can transfer to a larger scale. This is my last slide about isotopes used in the continental crust study. You will find, especially in the tectonic paper, this kind of diagrams where people are using in situ hafnium isotopes in zircon. Why? A technician loves this kind. Technician love this kind of data. This is because in a single crystal, you can have an information about the age of your rock and information about the origin, the initial isotopic composition. And you don't have to enter in a clean lab. In Technician 8, the clean lab, you don't have to do chemistry. You just have to mechanically separate your zircon, okay, do a thin section, put it in the machine. And then why, maybe you don't remember, why you can have directly the information about the initial isotopic composition in zircon. This is because there is no lutetium. So if there is no lutetium, there is no radioactive decay of something, and then hafnium should give you the initial isotopic composition. And this kind of diagram with ages as a function of epsilon hafnium is found now in many papers dealing with dating, because from a machine you can have directly in the same time the two isotopic compounds. And then if you have the initial hafnium, of course the precision is not that good, but you can replace the loss of precision you had thanks to the measurements by a statistical approach. You can make many dots in zircon. And when you go to chemistry, I show you on Saturday, it's a long process. So you deal with one sample, it takes 1 week to have a number. And then here you can have a lot of numbers. So maybe if the precision is not good, if you are doing a lot of measurements, then you can have an idea about the change in the epsilon hafnium. And typically, it's also what did Sophie in her paper. She did some dating, uranium lead dating, okay? And she did at the same time hafnium isotopic measurements in the different generation of E-type granite in a place in Peru. I will show you this tomorrow. And then she shows some changes, slight changes, statistical relevant changes in the osmium isotopic composition. And for example, here you have more crustal-like signature. So there is more input from the lower crust inside the magmatism, inside the magmatic isotopic signal. And here you have more mantle isotopic input in the E-type granite magmatism. But if you have changes in the isotopic signal in the same type of granite, I assure you, this is granite, this is granite. Means that the granite are not produced in a closed system. If it's a closed system, everything should have a crustal isotopic composition, because this is a crust. You melt, you create a crust, closed system. Okay, maybe the heating is coming from the subduction volcanism, but then it's independent. You have arc magmatism, which follow their own conduit, to their path to go to the surface, and then you have conductive heating of the base of the crust. It's melting, it creates granite, but it doesn't change. Should not change. Should remain exactly the same. And here we have the same granite exactly, but in the hafnium we have some change in the isotopic signal. We are moving from typical crust, not that much crust. Crust should be here, but there is still a very real crustal isotopic signal in the old time of this arc magmatism, and then we are moving with time. We have some change in the hafnium, so it means we have some contribution of the arc magmatism input and of the mantle, so to the crust. So maybe we have what we call crustal growth. We are creating, still at that time, creating continental crust. So this is very useful because in a single zircon you can have information about the age and about what we call the juvenile contribution of melt to the continental crust. And so I will show you tomorrow how we can deal with this kind of study and interpret them even if we cannot use the AFC equation and AFC process to explain the variation of the isotopic signal. We don't have this. We don't have this, but still we have this. So you need a process to explain the way we are producing some new section of the continental crust. So tomorrow, not today. Thank you. That's all for this one. So my next talk, normally it's a case study, but not about continental crust. Maybe I can switch directly to the Sophie Demouy thesis. But today, normally I've planned to tell you about continental volcanism. So what do you prefer? I have three. Maybe we can vote. I have continental volcanism, I have subduction-related production of granite, and I have oceanic ridges. So your decision or mine. Maybe I need to drink a little bit of water, but I prefer to do the continental volcanism. And it's okay? So let me check which one is it. No, this is not this one. Sorry, I have to find my... Yeah. Mm. Mm. Mm.
Are basically related to geodynamics rather than take it for the world average. Right? So I have a problem which I am facing basically in my work. You have subduction and you have collision. So you have two inputs and you do not know from where the granites are coming. So in such a case, what will be your problem? See, we have the Shook suture zone, which is the first suture. And
I understand.
you have the subduction into the Karakoram.
Yeah.
So you have a Karakoram batholith on one side have the Ladakh batholith, which is calcalcline,
Mm.
in the second peak. Now that is anatexis,
Mm-hmm.
deep anatexis.
Mm.
This is subduction level,
Mm.
calcalcline. Now we have a suite of granites that are within the suture,
Mm-hmm.
and they are all compressed within 1 kilometer.
They are I-type granites or TTG?
No, we do not know. They are not TTGs.
No TTG.
No.
Okay. So first, you have to remind that this is average continental crust that I show. Okay, that in average are fitting the arc-related composition, but in the average you have different end members. So you can have some granite, I-type granite, which doesn't show anything, very far from the average of the arc-relatism magmatism. Especially sometimes they don't display any niobium tantalum negative anomaly, and then you have to find another. You have to find about another source for this granite. So what are granite? Mainly they are produced. Either there are two hypotheses. There are differentiation products, so large differentiation of an alkaline magma, calcaline magma, or they are the product of melting of something like basic stuff, like basalt or metabasalt or whatever. So you can generate this kind of melt in different settings. The thing, my topic here was to deal with the global volcanism system. So the way I deal with in fact I did only one study on granite on the Peruvian system. Is I'm sure there is a subduction. Okay, so if there is a subduction, then I have no trouble about the origin of the granite. They are subduction related, maybe directly or indirectly, but there is a relation with the subduction. When you deal with granite in orogenic massif, this is more complicated because you have first to go back to the initial isotopic signal, which is sometimes tricky, and then the way I will deal with this problem is to have the isotope on one side, the trace elements, and then some idea about the tectonic regime, which is completely independent for the petrology and the isotopes. And if the two evidences are showing that there are links to something which is subduction related, exactly what you say. You know the setting of this granite, you know what happened, you know sometimes the collision, etc. And if you have two evidences which show that they are subduction related, then you can propose that they are subduction related. But surely, the isotope will not tell you directly that they are subduction related. No, not directly. You have to constrain your geodynamic setting by other kind of evidences.
The crustal shortening that has occurred
Mm.
is the problem. Because we are all juxtapositioned within this one line. So actually, do you think that we need to open it up?
Yeah. This is what I told on the first slide. This is why geochemists, there is so few study about in geochemistry, did not work with the continental crust, because you have to get rid about the history of your rocks. And in terms of isotopes, this is very complicated. So this is why the tectonician loves this kind of hafnium and in situ data, because you may think that the zircon have resist the different metamorphic event or even melting events they have encompassed. You can have like a zone zircon, and in the middle you think that the hafnium is pristine, but it's not. Or it cannot be the case, depending on the time the granite have sit, the melt or mixing melt with crystal have sit in the crust. If you sit them for a long time, maybe you can have a reset between the hafnium isotopic of the core and on the rim. This is a very complex problem. Okay. First you measure, you date, and then you try. Date is very useful. Date is very useful because if you reconstruct the story of your protolith.
The Ladakh is dated at 55,
Mm-hmm.
and these granites are also 55.
Mm.
The errors are slightly larger on the other one. These are very small plutons between the two batholiths.
Yeah. I don't have the answer. That's the problem. I don't. The only, yeah, I don't have the answer directly on this kind of process, especially granite. We will see tomorrow, because mainly they are not melt. You can treat them as melt, but they are not melt in terms of petrology. They are mixing between melt and crystals. Okay, so either you are using them as melt to make some model, or you can't. And so this is people from South Africa. They just published paper saying that you cannot compute any equation in terms of isotopic process. You cannot compute any equation dealing with melt with the granite, because there is perithetic mineral, and so during the fractionation history of the granite, you have this mineral carrying some isotopic signature, which go through the process with their own isotopic signature, and at the end you have a mixture between the isotopic composition of the melt and the isotopic composition of these minerals. So this is a tricky way to deal with. So let's switch to something completely different. We go into Africa. Okay, this was a PhD student of Philippe Nonot, a guy who is now the responsible of the mass spectrometer in Brest laboratory in the western part of France, in Brittany. Michel was in the jury of Philippe. Okay, so he knows perfectly what I'm going to tell about. So if you have questions, you can ask him too. So it was we did 2 field trips in Tanzania, one in 2003, one in 2005, because this is a very large volcanic system. Okay, and it was not sampled until the 60s. So at the end of the English, it was an English colony, so protectorate. Before the English were thrown away, roughly. So they came back into England with all their sample collection. So they did a very good job in terms of geology. But after that, all the paper, you should know that all the paper you have in North Tanzania, in all the volcanic system you have here, are paper from rocks which were taken from, comment on dit des tiroirs en anglais, Michel? Ladder? No. When you have sample in, the repositories. Okay. So we had the idea about maybe we can come back and sample and do some isotopic and etc. study, but we are with real sample, not for repository. And so it was the idea to come back. So briefly, the East African rift. This is one of the most famous rift system in the world. Okay, starting from the Aden Gulf and the Red Sea, going like this, and switching into 2 branches, tectonic branches here, the Western Rift, I will not talk about it, and the Eastern branches. And in terms of magma, the Eastern branches is stopping in North Tanzania here, okay? And this is where we went for sampling. The idea of the topic of this thesis is to see, maybe we can see in the magmatic signature, we can see an answer. We can find an answer about why the magmatism ends here. Okay. You have numerous shield volcanoes in this area. So the most famous are the Kilimanjaro, of course, but you have volcanoes like the Meru and Ngorongoro, very, very big volcano sitting on what we call in our study the North Tanzania divergence, because you will see that even here you have three attempts of propagation of the rift in this place. So it's a nice place. You have lions, elephants, also some Maasai. Sometimes they are not so nice. So it's a nice place to study, but you have to be a little bit careful. So some picture first. So this is all the sample we collect in this area. You see here the east branch of the East African Rift, and you have 3 branches here. Okay, here, here, and here, and all these big volcanoes sitting here. You have Ngorongoro here, the Kilimanjaro here, and on the middle you have many rifts, and you have the very famous carbonatitic volcano, but I'm not going to talk about carbonatite today. This is the Mount Meru. So of course, because this is large volcano, when you want to sample them, you have to climb them. And if you want to climb them in volcano in Africa, you have to deal with the Maasai villages, because this is sacred mountain. Okay? You cannot sample this kind of volcano if you did not talk first with the head of the village here. So because they are not talking Swahili, you need somebody who is able to talk Swahili and English, because I'm not talking Swahili, and also a guy who is able to talk Swahili and Maasai. So sometimes you have 3 persons with you, a Tanzanian geologist who is able to talk English and Swahili, and another guy who is able to translate Swahili into Maasai. But if you are nice enough with the head of the village, then you can access the volcano. Not the Meru, it's big, but you have tiny volcanoes sitting everywhere, which are very interesting to sample, and all volcanoes belong to a village. So, and sometimes when you come back to deal with the head of the village, he told you, oh, you are still there, you are lucky, because there is an old lion, you know, in this kind of, and so sometimes he's attacking people. But normally it doesn't tell you that before. So this is a famous Aldo-Inolen guy with a carbonatitic flow here. It's my wife, okay? But at that time she came with me because she was making some web page for a school in France about our expedition. So it was, we had the opportunity to find some money to bring her with me. She's sitting in the middle of the Ngorongoro volcanism. Of course, before coming here, she complained because I'm putting picture of her in my presentation, but I said no. That's the Ngorongoro volcanism. So this is Ngorongoro after a massive explosion, because it is a 10-kilometer area here, and before that there was a nice volcano like the Kilimanjaro, but everything was blown out, and so we don't have access to the historical lava flow, except the oldest one on the border. Everything was spread into the atmosphere, and I would not love to be there at that time. The crater island, this is also the volcano. So this is typically the outcrop you are finding there. So you have to deal with tropical vegetation, but you know this in India, okay? So you have to really check about where you can find some outcrop, and mainly in the rivers, in the small rivers, on the edge of the volcano. And so it's difficult to map, difficult to find the historical lava flow. But thanks to the English geologists and also the Tanzanian geologists, you can buy some maps there at the Geological Survey, which were not that bad. So you cannot find them anywhere than in Tanzania. You have to go in Tanzania to buy them, and sometimes they don't have them anymore, and they are drawing them for you with pencil, color pencil. So I have a very nice original map of the Tanzanian team. And the Kilimanjaro, of course, with eternal snow on the top until now. Climate change, we don't know. That's the Kilimanjaro. So this is Africa, not the Alps, Africa, okay? So, what about and I told you before, the subcontinental lithospheric mantle, and you saw the data in my previous presentation, can develop isotopic signature, which look like the isotopic signature you can find in OIB. Okay, and of course, because we are in a continental crust setting, we have to deal with continental crust contamination. And this is a major issue. This is a major issue when you deal with continental volcanism, because for sure you have continental crust contamination. And then you have to ensure first that either you can use your data or you can't. If the continental crust contamination is very big, then it's very difficult to get rid of it, okay? To come back to the original source-related isotopic composition, and then you cannot use them anymore to deal with the geodynamic setting. Okay, we'll see that later. So I will not go into detail for all the isotopic composition of all the lava we sampled there, because I don't have time, but I will focus on the Kilimanjaro because it's a nice example of what we can do with the trace elements and isotopic composition. So the second time we decided to sample again the Kilimanjaro, because the Kilimanjaro was not sampled since the 50s, and maybe we have the opportunity to make some nice paper about this volcano because it's famous, okay, everybody knows the Kilimanjaro. But the problem with the Kilimanjaro, it's high, and there is no road. It's a national park, so the only way to access the Kilimanjaro is climbing the Kilimanjaro. So when you are a tourist, it's cool. You have an expedition. Many touristic stuff are proposing you to climb the Kilimanjaro. But when you are a geologist, you need to collect kilograms of sample. It's not a touristic expedition. So you have to really organize this kind of expedition there, that you have to deal with 20 people carrying your food, because you are not going to spend 2 days, like 2 days climbing and 1 day going down the Kilimanjaro. You are going to spend 20 days in the Kilimanjaro without any road access, without any access to water, food, etc., etc. And despite of this, you need to collect kilograms of sample. Thanks to the Tanzanian people, and especially the people living around the Kilimanjaro, they are very brave, very, very brave, and they are very resistant. They can carry up to 30 kilograms to 35 kilograms of something in your backpack. I can't, okay? So when you are starting an expedition like this, you have to arrange with 1 or 2 guides, so they are hire people, and they will organize a systematic refeeding of food and water and rocks going down by the different paths of the Kilimanjaro. So when you deal with a geological expedition on this kind of volcano, you are 20 or to 25 people at the same time. 4 French geologists and the rest are Tanzanian, okay? And the way they are dealing, in fact, everybody is coming with the water and the food, and and then you replace the water and food by rocks. And when one of the carrier have a bag full of rocks, then he will go down in one on the path going down of the Kilimanjaro, bring your rock down to some place that you tell him, and then you have to pay him enough that he not throwing your rocks away and going back to his village, and then he will come back with another path with the food and the water, so you can stay at 4,000 meters on the Kilimanjaro to continue collecting your sample. So that's the basic map of the Kilimanjaro. In fact, Kilimanjaro is not one volcano, it's 3 volcanoes. You have the Shira volcano, the Kibo volcano, and the Mawenzi volcano. And you have plenty of what we call parasitic activity, basaltic volcano, okay, which are late expression of the volcanism. Everything you have a very nice orientation, and in fact it's corresponding to the moment of a major crustal accident fault in Tanzania, okay. And so the objective was to sample these three volcanoes, especially all the historical lava flow. So this is the sample position, okay, what we did. One on the top, unfortunately not me, I was sick. And so you say you are standing, because here you have a tropical covering, so you cannot sample, very little access to the lava, and so you are sampling on the top. So that's typically the top of the Kilimanjaro. Here this is the Shira, the oldest one, okay? So here Shira is mainly basanitic in terms of composition, typical thin section of basanite, with some nice obsidian layers, very beautiful rocks. For a geochemist, it's paradise because it's only glass. You have feeding dikes also, which are very interesting, very large feeding dikes, which are feeding the Shira cone. And you still can find here, it's 3,500 meters. You can still meet elephant at this high, okay? Or you don't want to meet elephants, depending if they are aggressive. That's the Kibo cone with snow, okay, and a glacier. So Kibo cone are very high. Typically phonolytic, trachytic to phonolytic composition, okay, on the field. And you have many different type of lava flow, historical. We try to sample all of them. This is our geological friend in Tanzania, Edika Fumeni. That's a typical one lava flow. Scale is normally one human is the size of my pointer here, okay? If you are sitting at the edge of the lava flow, it's like this, so it's a huge lava pile. Of course, you are not impressed. You have the decanter up close to here. It was my first time close to such a large pile of basalt. Okay, you have an example of phonotephrite, or tephrite, I don't know. And the Mawenzi. Mawenzi is more trachybasalt composition. And here again, you have my wife here, sitting on the Mawenzi dike feeding system here. This typical shape of the Mawenzi, full of dikes of trachybasaltic composition. And then the last type of volcanism you can find on the Kilimanjaro are what we call the late parasitic activity, and typically basanite, and if you are lucky, full of xenolite. And it's well known, not on the Kilimanjaro, unfortunately, but on the side of the Kilimanjaro, you have a lot of basanitic cones, little parasitic cones, full of xenolite. Very beautiful one, which were studied a lot in the past. And so this is a basanitic composition, typical, full of clinopyroxene, you know, this very huge dark clinopyroxene. So first what we did is unspiked potassium argon dating. That's not my specialty. We did that with collaboration with Hervé Guillou in Gif-sur-Yvette in Paris. And so it's a very specific way to use the potassium argon dating because it's unspiked. It's typically devoted to date very young events, okay? And it's typically adapted to the Kilimanjaro lava flow. And so we date again because there were very little ages on the Kilimanjaro cone. And to have an idea about the chronology of the different volcanic sequence, you need ages. Not this time for age correction of the isotopes, but for stratigraphy of the volcanic eruption. Okay, so typically the age are for around 500. No, the oldest is the Shira with 1,900,000, 1.1 million year, and the youngest, of course, is the top of the Kibo here, with an age of 227,000 years. So you principally you date the glacis, the ground mass, and not the minerals inside. You separate the ground mass physically, and you do the potassium argon on the ground mass. So we made a paper on this, but then we measure all the major and trace elements. Typically what you do in a geochemical study or petrological study, you do the thin section. If it's needed, you do the dating, and then you are measuring the major and trace elements. So we are typically in the phonolite theory here from basanite to phonolite. And here you have the different isotopic, the trace elements pattern for the different cones of the Kilimanjaro. And so what you have in terms of trace element concentration, you have, as I told you in the beginning, same type of trace elements enrichment that we find in the other volcano in North Tanzania, but you have some specific anomaly, which normally you don't find in OIB. Okay? So, what are these anomalies in the Kilimanjaro? You have a slight depletion in the most incompatible element, rubidium and cesium. Okay? No battery anymore. Okay, I will use my pen. Here. Most incompatible. You have some negative anomaly in potassium, strontium, and titanium. Okay? And you have sometimes a slight depletion in zirconium and hafnium. So forget about zircon. We are in continental volcanism. We deal with magma, which are extracted, basaltic series magma, which are extracted from the mantle. Okay? There is no crust, nothing. We are dealing with mantle stuff. Regarding the Kibo volcanism, you have two different types of signature. You have a very, very strange signature with a very big anomaly. We call it the Kibo 1 signature, okay? And you have a large thorium, niobium, tantalum enrichment here, but it's relative enrichment. You have still the potassium, strontium, titanium negative anomaly. And you have also some heavy rare earth elements fractionation, but not for this one. Here, forget. Typical. Sorry, it's important. You have heavy rare earth elements fractionation. And if you remember what Michel Gregoire told you, heavy rare earth element fractionation are the garnet signature. Means they are coming from deep. Means they are coming from deep. So, how can we explain this kind of signature? And the parasitic activity. Same. Very incompatible element depletion, negative anomaly. So you say these three features are systematically found, okay, in the Kilimanjaro volcano. In terms of isotopic composition, they are sitting apart from one sample in the Shira, which is very enriched, have an enriched isotopic composition, or are sitting in the very small craton here, and that's typically the problem we have when we deal with isotope, when there is no big spreading of the isotopic composition, is when all the samples have very close isotopic composition, then it's very difficult to interpret what can be the difference between one lava flow and the other, because they are the same. Okay, so there is some spreading, but not that much, except from one sample from the Shira. So, what we first had to solve is the problem of crustal contamination. Because if you read the literature about continental volcanism, and even if you read the literature about the volcanism in North Tanzania, people always talk about continental contamination, continental crust contamination, and the effect on both trace elements and isotopes. And then you have to check if you can use your elements, if you can use your signal to tell about the origin of your magma, or if you can't because you are only seeing continental contamination. So, sorry, oh, it's on the top. Typically, in a diagram like you see on the top here, if you have a trend between the isotopes, isotopic composition, and the fractionation index, here you have SiO2, see, on the y-axis, same SiO2, on the x-axis you have strontium and neodymium. If you have a trend between the isotopic signal and the fractionation index, then you are dealing with something which look like fractional assimilation, fractional crystallization, because you have contamination of your sample. And you see part of the sample, the triangle, for example, in terms of strontium and neodymium, there is some trend and logic between the SiO2 and the strontium, and SiO2 and the neodymium. And so the first thing we did when we had this number is to compute the effect of the AFC, assimilation fractional crystallization, knowing what we know about the upper crust and the lower crust. We compute the process of assimilation fractional crystallization, taking a basanitic primitive lava that is supposed to go inside the crust, assimilate, fractionate, and then reach the surface. And this is typically the line you have here. Here, this is the range of trace element signature you can have in the parental melt, basanite. Here we imagine two cases, and then we compute the different lines. The line you have here is AFC process for neodymium, strontium, and trace elements. Because this is something I did not tell you about, but you can also compute the AFC process using the trace elements. And using different type of contaminants, using different type of sources, we were able to reproduce the majority of the trend we see in the volcanic lava flow. So the question is, can we use, if the signal is buffered by the AFC, means can we still use the isotopic signal to tell something about the origin of the lava, or do we have only to do with the contamination, and then we have to get rid about the isotopic data to tell something about the volcano? So finally, what we propose, but it can be discussed, is that we still can go back to the different type of sources, computing this isotope, and then we can use these different type of sources to tell something about the origin of the volcanism. That was the topic of the second paper we did on the Kilimanjaro. But that's something which can be criticized, okay? Regarding the melting process, this is two different ways we compute the melting process to have an idea about the origin of the lava. So first, we deal with the isotopes to come back to a source which is the mantle in terms of isotopes, and we deal with the AFC. And then when you subtract the AFC signal to your magma, then you can deal with the parental magma before the contamination. And then you can compute some melting equation to check what kind of source can be at the origin. And this is typically what are plotted here. We compute some primitive and depleted sources, and we compute some fractional crystallization trend to explain the triangle here on the top, which are the Shira volcanism, and the square and the diamonds, which are the Kibo volcanism, and the Mawenzi will be the circle which are fitting underneath. So we explained that two types of sources, primitive and depleted, can explain the vast majority of the spreading we have in terms of trace elements in the lava, but you have to deal with fractional crystallization and, of course, associated to crystal contamination to explain the most differentiated magmatic theory. And the spreading you have here in terms of trace elements, and cis like you, is not related to fractional crystallization, is not related to partial melting, is only related to the abundance of phenocryst or xenocryst you have in the lava. You have to know that trachyte, phonolite are lavas which have a lot, especially trachyte, a lot of phenocryst. Abundance of phenocryst is huge. And if you have a lot of phenocryst in a lava, then you can change drastically the trace elements content. It's a dilution process. If you have in a melt, you have a lot of feldspar phenocryst, yet you can change the trace element concentration and also the isotopic composition. And this trend here is only related to the abundance of phenocryst in the melt. Okay? So this is typically porphyritic lava and apheric lava. They are sitting on a trend which is only related to the abundance of phenocryst, and it has a dramatic effect, for example, on the concentration of samarium. So when you want to deal also with the parental melt, you have to subtract this kind of effect on your melt. To compute this model, we use some idea which were published already by Andreas Speth in some volcanic theory, not far from the Kilimanjaro, and some idea which were also proposed by Francis Eluden and Anton Leroux, and which suppose that you have two types of mineral which are stable in the source, amphibole and garnet. Okay, competition between amphibole and garnet. And to have this kind of mineral in the source can explain the majority of the trace elements anomaly I present you previously on the spirogram. Okay. So what we did is, first we have the lava, we analyze, we subtract the effect of the AFC, we subtract the effect of the fractional crystallization on some which have no evidence of contamination, and then we did a reverse modelization of the source to deal with the source which is the occurrence of amphibole in garnet. So typically it's a garnet and amphibole bearing lertholites. Now what you have to solve is either this source is related to a plume or it's related to the subcontinental mantle lithosphere. So amphibole, it's a tricky mineral because it's difficult to imagine that it's really sitting in the plume. So at this time we favor an origin in the subcontinental mantle lithosphere. And in fact, this is consistent with the evolution of the isotopic composition with time. So here, on this diagram, you have the age on the x-axis and the neodymium isotopic composition, okay, not corrected from the AFC, the normal isotopic, what we measure, corrected from age, but not from the AFC. And you see that the spreading of the data is changing through time. The old volcano, the Shira, which is the oldest, okay, sitting there, can present some radiogenic strontium and unradiogenic neodymium, so what we call enriched signature. And when you go to 0, okay, you have the Mawenzi then with intermediate signature, and when we reach the Kibo, you have signature which are more mantle related, depleted in terms of isotopic composition. And if I have plotted here this diagram, is you have to imagine that the system under Tanzania is a plume interacting with the base of the lithosphere. So either you have melts which are directly reaching the surface, or you are melting this. And the problem, if you have a logic of age with the isotopes, it's difficult to imagine that this variation in isotopes is only related to crystal contamination. Only. Because if it's related to crystal contamination, normally you should have the same spreading or random spreading and not logic with time. So how to explain this variation with time in such a geodynamic context? So we propose for the Kilimanjaro and also for the whole Tanzania that you have two steps for the generation of continental volcanism. You have what we call a cold step, old, and a hot step. That when a plume is tapping the base of the subcontinental mantle lithosphere, the conductive heating can trigger the melting of this lithosphere. And this lithosphere have recorded a enriched signature for a long time, okay, have developed its own radiogenic signature that you find typically in the Shira volcano, the old cone of the Kilimanjaro, okay. And through times, if the plume is still impacting the base of the lithosphere, you can refertilize this part of the lithosphere. And then if you refertilize this part of the lithosphere, after a certain time gap, and I don't know if you remember, there is a very big time gap between the Shira and the rest of the Kilimanjaro volcano. The first one was 1.9 million years, and then after you reach 500,000 years. So it's a time you need to refertilize the base of the lithosphere. Then you can remelt it, but then you will not have a typical subcontinental mantle lithosphere. You will have, in terms of isotopes, a mixing between the signature, which was already there, and the signature brought inside the subcontinental mantle by the plume melt. And this recorded and created lithospheric mantle isotopic signature, which were expressed in the Shira volcano, and of course is concordant with garnet and Fibol ratio in the source, stabilization and the deep depth of the source. And the Kibo, for example, lava, which are much more giving an isotopic signature related to a plume, okay? Because you have a plume component which is really inside the signature of the melt, despite any crystal contamination. Of course, you can discuss this data in another way. This is of science. You can discuss this data and say, no, I disagree with you. This is only the plume melt metasomatism which trigger melting. The only difference you have in a Shira compared to the other is you have more crystal contamination for the Shira than you have for the Kibo and the Mawenzi. So in our paper, we discuss this hypothesis, saying that, okay, maybe, but if you look at the major element composition and the type of lava you have in the Shira, they are very primitive, basanitic. So they did not suffer a lot of fractional crystallization. So how you can explain a lot of contamination of lava, big contamination, crystal contamination of the lava during fractional crystallization, if your lava are not fractionated? If they are very primitive, then you have little fractionation, so if the process for contamination is assimilation fractional crystallization, then no, you cannot explain enriched isotopic signature by this process. So that's what we propose for non-Tanzania. So to come back on this setting, now if you come back on the North Tanzanian rift, maybe it was because you have a very old cratonic block here, blocking totally the propagation of the rift, and under this cratonic block you have a large portion of cold old lithospheric mantle, which have developed this radiogenic signature that you find in the oldest volcanic cones here. This craton is impacted now by a plume. So the first evidence, the first trace of volcanism you find in this place are remelting of this lithospheric mantle, and then if you melt and then you refertilize by metasomatism, then you in fact delaminate the mantle. You are eating it, you are making him more sensible to propagation of a rift. So in fact you are consuming your craton, you are eating it, you are digesting it by a plume. So you need some time for digesting before you can propagate the rift to the south. And this is why we know that there is a big, what we call the Tanzanian craton, okay, just south of the Kilimanjaro, etc. And so this Tanzanian craton was blocking the rift, and now we are seeing in the last volcanic event, we are seeing the trace of the first plume melt going to the surface. That means that maybe the mantle is ready for rift propagation. And in fact, we know that in the eastern part of the Tanzanian divergence here, come back on the first slide. Here, we are now seeing some trace of the first type of volcanic activity. There is some volcanic activity happening now here. Okay. So maybe all this time was devoted to erosion or remelting, fertilization, temperature increasing of the cratonic mantle to let him be ready for the rift propagation. And so what we propose in the paper is that the last volcanic event we see in Tanzania are really related to plume melt, and that maybe there is no trace of the lithospheric mantle in the isotopic signature. Not for Kilimanjaro. Still Kilimanjaro, you have plume melt, but for the basanitic activity, maybe we have some direct trace of the plume. And I think it was my last slide. And also it was fun to be there. Yep. Thank you. If you have questions? Remember, it was my PhD student work, not mine. Huh? And mine also, but it was Philippe Nonot. Question? Yes?
You showed isotopic data
Mm-hmm.
for your lavas.
Mm-hmm.
They're obviously trachyandesite phonolite series.
Yes.
You know that prior to this event, we had the Chilwa alkaline complex,
Yes.
which is Cretaceous.
Before that in Tanzania?
Yeah.
Yes. With little access to this one. Huh?
Okay. So
Kimberlite, you have access on with.
not kimberlite, but carbonatite.
Ah, yes.
To show the EACL diagram, you have the isotope for the East African.
The general diagram, yes.
Yeah, these ones.
Mm-hmm.
So your samples plot discordant to the EACL.
Discordant? Yeah. A little bit on the top, yes.
This is the EACL.
Yeah, yes, I know.
This is the EACL.
Yeah.
So your samples are plotting
Yes.
discordant.
So, yeah. So you want me to explain this one here?
I mean, for my understanding,
So, for me, this one are contaminated, continental crust contaminated, especially by upper crust continental crust. That's the way we explain this one here. Okay, so because that's a typical problem I told you with continental volcanism. You have to get rid about, even for the Kilimanjaro, it was not that easy to publish the isotopic data and to use them to deal with the geodynamic context, because there are many papers, especially papers using lead. This is why we did not perform lead on this lava, because lead, they are very, very quickly switch to the contaminants. But the problem is to make into balance the crustal contamination and for different isotopic system, and to use them to say, okay, maybe it's the isotopic composition of my sources. So that's typically the case for this one. So this one, we interpret them as the result of lower crust crustal contamination. So unradiogenic strontium, very and unradiogenic neodymium. Huh? And what?
Sanitization with the carbonatite.
Ah,
The subcontinental
but we did not make.
lithosphere.
Ah, yeah. But
So
normally in the
sanitization, because
but normally in the carbonatite you should switch strontium to. Yes, no way you can.
but if naphthalene separate, then
Yeah, but normally isotopes they should be homogeneous between the differentiation. Yeah, no. In fact, I did not work on the carbonatite. Huh? It was another subject, and we decided not to work with this one. But you know, some sample from the Kenya rift, they show also this kind of spreading. And so, yes, I know that people have proposed that the separation between the nephelinite and carbonatite can be an issue to explain about the isotope deciphering, but for my purpose, this is related to crustal contamination, definitively, especially in Tanzania, because apart from the lengai, when you have carbonatite, the other are typically belonging to the basanitic series. We have one nephilitic volcano, and but it's not this one. Yeah, I did not present it there. Of course, you have completely different isotopic composition, but it was not used because this nephilitic volcano was here. So slightly different context, okay? And you have to also to know that the lengai is not in the divergence. It's really inside the rift, okay? It's the Tanzanian craton is here. Lengai is in the rift system. There is no craton below the lengai. This is why we were talking about mainly cratonic lithospheric mantle for the source of this lava. Very nice field. It's so beautiful, this area. Even if you have old lions sitting somewhere in the hills and your guide is not telling you. Once we get out of the car, and all the Tanzanian, our guys from the geological survey, the two drivers, stay in the car, and we just went on the field. Huh? Yeah, not tigers, lions. And so we were going on the field, and when we came back, in fact, they were sitting in the car with the closed door and say, why didn't you join us? Because they say there is an old lion in the hills. And they did not tell us. So after that, when we went out of the car, we just check if they are coming with us or not. Yeah.
We have similar problems with the rare Mudwara, access in India.
Mm-hmm.
We don't have anything with garnet calculation,
Mm-hmm.
unlike like this.
Mm-hmm.
But we have tachybassalite,
Mm-hmm.
bassalite, tachybassalite,
Mm-hmm.
and some mixed and
Yeah, and something like this I would like to, I forget to explain about this. This phonolite without, but there is garnet inside. This is only fractional crystallization and large fractional crystallization of feldspar, and also the occurrence of the feldspar phenocryst, large abundance, okay, in Kibo 1 phenocryst that wipe out the garnet in nature. So yeah, this is why I compute here. So I did not show the effect on the heavy rare earth elements, but you can wipe out the effect of garnet in the source only by either fractional crystallization or the occurrence of phenocryst or xenocryst. Other question? So tomorrow we will go in South America, in Arequipa, in Peru, for the subduction. It will be the thesis of Sophie Demouy, who is now teaching in secondary school. In fact, she left geoscience, but she's teaching in France, secondary school. And the second topic will be about the Indian oceanic ridges. And you will have some nice picture of, because we dive with a French submarine there to collect the rocks, and you will see some nice picture of the bottom of the ocean taken by the submarine. So come back, please. Even if you have passed your exam, come back. Thank you.
so that's the end of the lectures for today. But we will come back at 2:30.
Sorry. No. Okay. Good afternoon. The topic that I am going to speak on today is about what are the minerals that can be used for isotope studies, for dating, for example, right? And this should have been preliminary to talks by Matthew, but we will see it now, right? So we already spoke of an error chron or an isochron,
And as you have noticed over the week, you are finding that not everything can be answered by powder geochemistry. The answers to most of your questions will come in a logical way from the field first, from the optical microscopy, from your major and trace element characterization, and if the need be, from your isotopes. Practically in many areas, especially in the regional or the local context, there is not much variation in the isotope, and therefore if you have an isotope problem, you need to predate it by an understanding of what you would sample in the field. So you never ever decide that you are going to work on isotope until you find something in the field. If you have this prefix idea that you would go to the field to collect samples for isotopes, then you are on the wrong lane. It's always field followed by petrographic characterization, geochemical characterization, and if you cannot answer the question within the realm of these investigations, you resort to isotopes and high-end chemical analysis. You do not use isotopes simply because you have an instrument or you have an access to instrument. You have an isotope problem only when you have a specific objective, and that objective most of the times is decided in the field. So there is no substitute for field work, and of course you can, but when you are in the field, you have to understand, besides your specialization. For example, she is a sedimentologist, she can wear her sedimentary cap and she's deciding facies. Similarly, someone from metamorphism, you have seen about mantle petrology. But the fundamental block for isotope, trace element, budget is minerals. And if you have the mineral, it's not necessary that you can date. If you have the mineral, it's not necessary that you will be having a mineral separate and a mineral isotope. You have to have a suit, okay, and the concept of cogenesis comes into place. Now, cogenesis or cogenetic rocks are decided in the field. You must know the relationship between one rock and the other. For example, in the Precambrian, you have many different rocks. They may be of the same age, but they may not be cogenetic. That means they may not form from the same process. It's a mere coincidence that rocks from the Deccan and Rajmundry and elsewhere in the world are Cretaceous. Just a mere coincidence. Is the glaring example of how argon-argon or potassium-argon has been violated. 98% of the dates published have been withdrawn. of the dates published are withdrawn, and therefore you have to have this genetic connotation in the field. Now, if we have made this as the thumb rule for isotope, you don't have the objective before you go to the isotope. Then you must know what you are dealing with. Material. And so we have seen that we have mineral dates or mineral isotopes or mineral separate isotopes, and we have whole rock. So when to use mineral and when to use whole rock, or when to use them together, is at the discretion of the user, right? And many a times we forget to address that issue, right? So based on your specialization, whether you are metamorphic petrologist, whether you are igneous petrologist, or whether you are a sedimentologist, you need to understand cogenesis. For example, in sedimentary, because many of you would like to be in sediments, what can be dated, what can be isotopically characterized, and what can be a significant isotope number, right? So if you go into the process of sedimentology, you will have minerals that predate the sedimentary cycle. You will find that some minerals develop during diagenesis, some minerals that form by the process of orthogenesis. So you have pre, syn, and post sedimentary minerals within one cycle of sedimentation, and they could extend for over millions of years with overlaps. So what are the telltale minerals? What are the minerals available for dating? What are the minerals that can be used for isotopic characterization? And what is the petrogenesis in terms of putting them together and interpreting? That is what is the precursor to isotope geology. We have several minerals that can be dated and several minerals that cannot be dated because they are poorly behaved or badly behaved. So you can have a mineral that is dateable, but the mineral may not be a good boy or a good girl. They may be very bad. So you have to know how to identify this. What are the instrumentations that you require? So not all zircons. So for example, if you take granites, then this is what everyone knows, even in NGRI. People collect granites. So they're collecting 5 kgs, 6 kgs of granite, one sample or a couple of samples. They crush them and they separate zircons. They separate either by heavy mineral or by magnetic separation or simply mechanical. And out of that you get something like 7,000 zircons, but you will end up selecting only 25. So these chosen zircons need to represent, as Matthew says, the entire batholith, for example, the entire spectrum across the Concordia. And so choosing the mineral is a tough job, although it is an ignored part of it. And what instruments do is, like we all famously know, garbage in, garbage out. So the instrument, like Matthew said, will produce a number. No matter what you do, if the instrument is on and you put a material in, it will give you a number. But whether that number is significant depends upon what you do prior to going into the clean lab or during the clean lab. Afterwards, error propagation, and you have seen the mathematics related to it, is very difficult to control, and you are not satisfied. So we have certain minerals in the weathering or in the paragenetic cycles that are indicative of the trace and the isotopic budget, plus project नहीं होता नहीं इधर प्रॉब्लम है, प्रोजेक्ट होता नहीं है. I'll try, but it doesn't happen. It doesn't work with this file. It doesn't go. Sorry. So in case of rocks, as we know, exotic minerals like diamonds, they cannot be dated, though they are carbon bearing, and the carbon stable isotope you cannot use to date a diamond. You require a mineral that is well behaved, that contains the father son, because it's a French paradigm, or the mother daughter ratio, and that the mineral is resistant to weathering, that does not exchange its isotopic systematics with its environment, that is fairly mechanically resistant and has self-annealing properties. That means if a mineral breaks because of tectonics or other thing, it should have the property to anneal itself. One very important mineral that anneals itself is zircon. And an emerging field in geology, emerging subject is zirconology. So a lot of people are now dedicating their efforts to understanding and studying zircons, not only for the UPBH method, but for other things. And we have superior materials like badylite, for example, better than zircons. So what we need to understand here is, if we need to understand isotopes, or if we need to understand dating, then we need to understand the morphology of the mineral, its chemistry, its internal dynamics, its trace element budget, and worst of all, its crystallography. Because minerals like monazite, apatites, they have selective absorption of trace and RE elements on certain phases. And so the concentration of your trace element budget is high on one phase and low on the other. So you need to have the high phase so that the detectability is better on the instrument. So very humble beginning is to begin with optical microscopy. So many of these minerals, I was not there for the lecture on the UTH method that Matthew spoke about, but we know that several minerals can be dated. And the method of dating is an intrinsic property of that mineral. Take for example a granite. A granite will contain 4 or 5 minerals that can be dated, or one granite, Matthew was speaking about I type of granites, will have a certain geochemical affinity and a signature. So you can have a monazite, you can have an apatite, you can have a biotite, you can have a hornblende, and you can have, say, rutile or sphene that can be dated. So the choice of the mineral that you date depends upon the process that you want to study. It's not on the presence or absence of the mineral, it's the process. So when you are going into the field, if you have a process related objective, then you will look for a particular concentration of mineral that suits that process. So there are certain properties of the mineral that are intrinsic to that mineral. So the first thing is presence or absence of the mineral. Second is whether it is well behaved, it does not have fractures, cracks, it is a closed system in terms of its isotope, in terms if it is metamorphism, that there is no loss or no gain, that is not affected by fluids. and these minerals can be taken for isotopic, single mineral isotopic characterizations, or for dating. So we'll just switch this slide and we will go to another talk that we said. So these are exotic minerals that can be dated: apatite, monazite, zircons, and we'll come to them subsequently. But we deal with very common minerals that can be dated, and those common minerals are sufficiently robust to garner our isotopic budgets, trace element budgets, and isotopic systematics. The first concept that we need to understand in terms of our trace element budget or on our dating is the concept of stability of minerals in terms of their crystallization in case of igneous petrology, in terms of their phase transformation in terms of metamorphism, or in case of Gauri here in terms of their diagenesis or orthogenesis. So you can have a mineral, for example apatite, that has different temperatures of formation. If I am working with a phosphorite or a limestone, then I can still have colophane and I can still have apatite. I can have apatites in granites. I can have apatites in, say, any other rock, basalts for example. Or I can have apatites that I can use for constraining tectonic uplift. So the technique of what I use the apatite depends upon my knowledge of the apatite and its paragenesis in terms of its formation and in terms of its geodynamics. Let us take one common mineral that can be dated and that controls the trace element budget. So the rock normally contains biotites, and biotites can be range, the stability of biotites can be across ranges of temperature, right from upper zeolite facies to say even granulite facies. You have biotite rich rocks. So the entire gamut of temperatures from 100 degrees to say 1000 degrees or 1200 degrees is possible by the same mineral. But there is a concept called closure temperatures. That means for an isotopic systematic you require a mother and a daughter, and of course you require time to disintegrate. Matthew, for example, was using potassium argon for dating his youngest lavas in Kilimanjaro. Though other minerals could have been present, but he was relying on whole rock potassium argon. Why? Because the resolution is very small. So you require sufficient time for radioactive disintegration to use other methods, though other minerals will be present in the rock. So the concept of closure temperature is the most important concept in dating, that is in situ LA-ICP-MS dating, as well as dating whole rock or dating individual minerals, right? So for example, we are talking about biotite. So biotite can be diagenetic, it can be metamict in metamorphic. The seniors probably know what is metamic minerals. The juniors have to be introduced to it. So you may have a biotite, but the biotite is in phase
Another student had asked a question, what happens in zoning? What happens if the mineral is twin? Right? So what we are trying to understand over here is there are many properties intrinsic to a mineral before we decide its name. Right? So these are good examples. For example, biotite or micas, you can see muscovite can be dated by the rubidium function if you know the temperature of formation of your muscovite. This muscovite, for example, 500 to 300 could be from pegmatites or could be from metamorphic. This is the realm of the pegmatites. But you can have biotites or muscovites that can be used for argon. Right? What is the range of that temperature? 300 to 400. What would that be? That could be metasomatic. That could be cooling agents. So you have a biotite. That does not mean that the biotite gives you a crystallizing age. It can be 3 million later that the biotite has crystallized. And therefore, you have to understand. And how will you understand that? That you will understand simply by preparing a thin section. And that's why there is always a phase difference between powdered geochemists and
So what Matthew was saying is the KDs, right? The coefficient of dissociation. So the coefficient for dissociation for plagioclase, say AN content 89, will be different in a melt crystal equilibrium, and for metamorphic diffusions the KDs will be slightly different, and therefore all of the isotopic systematics will vary depending upon the genesis of the plagioclase, whether the plagioclase is metamorphic or whether the plagioclase is igneous. Also, you know that metamorphic plagioclases have different laws governing their twinning, while igneous plagioclases have different laws governing their twinning. Let us take an example of a plagioclase that is zoned. So the KDs in a magmatic system will be different during the entire history of the crystallization of the plagioclase. You can have calcic cores and you can have sodic rims, and therefore the coefficients can change with increased fractional crystallization. So elemental zonings will decide
whether the rubidium or the strontium, for example, will have different diffusibilities. And that will govern, and then the modal abundance of your plagioclase will govern the isotopic signature. So therefore, my point is that you need to understand the process prior to going on or switching on to the isotopic systematics. Have I answered your question? Right? You have another question on that? Same things with biotides. Biotides can be zoned, they can be metamixed, they can be transitional, okay, or they can be also altered, right? So without determining that, you never put your mineral into the isotope instrument. It's very clear that it is better to preempt your errors than commit them and try to rectify them. Right? So what we are going to do is that we will see these minerals in hand specimens for practicals. We will see them in thin sections during our coursework also, and that time we will discuss the intrinsic properties of these minerals and how they can be dated. Calcite, for example, the uranium thorium method can be employed for stalactites, they can be employed for other things, right? So, but there the process is precipitation dissolution. Okay, so even the pH can change your isotopic systematics over there. So in acidic environments, you will have a different ratio of uranium and thorium, and so this fluxing, because uranyl ions are normally water soluble, and therefore, yes, the precipitation. So if you have stalactites which is zoned, then in that case you will get. So the calcaretes will give you, again, if they are hard pan, they can give you some variations. But if it's calci, then it's not a closed system. So they will always leak, to this thing. But if they are hard pan, or if they are, even rhizoliths will give you a lot of this thing. Yeah, they will give you different isotopic ratios. So rather than grinding your sample and homogenizing it, right, like what Matthew was saying was for hard rocks, you normally grind the whole sample and homogenize it by coning, quartering and all for the whole rock. Mineral separates, of course, are different. But in sedimentary, you have to think sedimentary and then isotope, because you are then trying to look at the process. So if you take one stalactite, for example, or one calci, it may have a totally different isotopic signature than the other. Therefore, you will have to treat them as individuals. So that sort of material you can think. So the most common methods that we use are basically potassium argon and the argon method. Okay, and they can be applied to environmental samples. They can be applied for archaeological this thing. So what are the potassium bearing minerals? Can we get some answers on this? What are the potassium bearing minerals that can be dated? Of course, biotites, muscovites, then K feldspars, that is orthoclase, sanidine. But sanidine has a problem. Very high temperature sanides cannot be dated because they are open. What are the other potassium minerals? Which are controlling the potassium, even the radioactivity for that matter. Clays. Most of the kaolinite series of clays contain a lot of potassium in them, right? And of course, amphiboles. You have richterite, right? You have many amphiboles that are rich in potassium and sodium, and these can be dated by the potassium argon method. That we will see tomorrow, right? We will see the potassium argon method, systematics of it, and a little bit, because this course does not have the component for dating, right? But we must go in that line because we have to understand the coexistence. So to sum up, what I am saying is that you need to assess the requirement for isotopic study, radioisotopes. For stable isotopes, they are totally different. But for radiogenic isotopes, you have to have a suit of rock. That means you should have at least 10 to 25 samples that you can put into the date. And they have to be well behaved. For that, it's a big task. If you notice Matthew's plots for isochron, rubidium, strontium, they are only 5 or 6 plots. Because finding a good candidate for dating is the most important and most difficult part of your isotopic systematics and of course dating, right? So what you need to know is cogenetic. That means in the field, for example in granites, because I know the example that way, you must know that the granite is coming from one parentage. You cannot have, and that's what we were discussing during the talk, if there are two tectonic zones culminating in one place, then you have to know which granite is from which tectonic regime to put them together on the isoplot to create a discordia. That you cannot resolve by stable isotope. It has to be resolved in the field, right? So you have to have a leading magmatism and a trailing magmatism. Do you get? So in case of the Deccan traps, for example, I would like to have an early phase of alkaline activity or basic activity. Then I will go on to the main phase of activity, and then I will go to the terminal part. So I will take, say, the precursors, that is the picritic lavas as precursors. Then I will take the main tholiites as cogenetic. Then I can take the lamprophires, which are post-cutting the flows. That itself is telling me that they are older. Okay, and then I can go to the differentiates. Like for example, I take the Dongri rhyolites, or I take Amba Dongar. I take the lava flow that is sitting on Amba Dongar, because I know that the Amba Dongar lava flow is 55 millimeters. And therefore now I have a cogenetic suit of rocks. So if I have to have trends on my isotope fractionation, then this is the kind of suit that I require. If I am looking at a very narrow spectrum of rocks, then I do not employ isotopic systematics. Suppose if I am studying the flows from the Western Ghats, then the strontium may vary in terms of its content, but the neodymium is going to be constant. And therefore, I cannot constrain the evolution of my rocks. But if I have, for example, a case which Savea is probably studying now, in which there are Cretaceous dikes and they are entrained by earlier TTG lavas and assimilated, then I can use isotopes to constrain, because I have two end members here. One is continental crust 2.6 billion years old and Cretaceous, and therefore I will get a range of isotopic characters which I can talk about and characterize assimilation, mixing and continental contaminations by contamination. So if I want to do this study, I have to begin thinking prior to the field stage. Okay, so these are two examples I am giving you where yesterday we were discussing with Shilpa ma'am and Gauri ma'am, and they were saying how. In case of sedimentology, the entire stratigraphic column is punctuated. It was done on the basis of paleontology and then ratified by two methods on the radioisotopes. One was the rubidium strontium method. So every formation, every era, every period on the periodic table has a standard rubidium strontium value. And then it was re-ratified by the potassium argon method. So every formation therefore has different end members, but they are characterized. Now they are being characterized in terms of stable isotope, oxygen isotopes, and of course much more superior argon-argon method. So even the stratigraphic numbers, they were quantifications 155 million years. Now they are going to have dates or numbers, right? So that's what you can start putting onto the Proterozoic rocks or putting onto your even Gondwanas for that matter. That you have dates, you have minerals that are datable, and they are well behaved, because that is the biggest violation in earth sciences. Practically every other paper has non-well behaved minerals that are put for dating. And so it's not the instrumentation that is important, it's the choice of the mineral, the choice of the method, and the choice of the objective that you want to solve, that determines trace element budgeting and isotopic systematics, right? So we stop over here. Of course, we'll see the systematics later on, and we can see a couple of examples, but the course finishes on 16th, and so therefore we will restrict ourselves, but we'll carry on these applications and lecture series during our coursework in the MSc and in the classwork and in the practicals, right? Thank you very much. If there are any questions, I would like to take it. You got the printout? Okay. Take it. Any questions? Yes.
What is about layered market conclusions? Should you prefer isotopes dating?
No, why should I mean, see, dating is, you date one rock and you know that the rock above it is younger and the rock below it is older, right? If it's a normal order of superposition. So what is your question?
Say about tectonic.
See, that is exactly what I am saying. What Matthew showed you was errors, right? He showed you errors. So what we are not taught to teach, suppose if I say 65 million. So does it mean 65 million? No, it doesn't mean that, because there is an error. If I say 65 plus 5 million years, so what it could be? It could be 60 million or it could be 70 million. Now that's 10 years that the sample has done. Right? So this is what he was trying to project that day, that your sample lies over here, this axis is this much in terms of time. In terms of resolution and precision, it could be like this. Right? So when we do it for the next semester, we will talk about errors, then we'll talk about, so it constitutes a constitution. So errors are like this. 1 sigma and 2 sigma, it's the closeness of it. The closeness of it. Right? And that is dependent upon 3 things: precision, accuracy, and human errors. And that has to be established for the lab by repeatedly analyzing the same sample. Yes, ma'am. Okay. कल ही ना उनका होने के बाद कल नहीं, he is not there tomorrow. He is going. You don't know, so we can't do that. Day after tomorrow. Valedictory के बाद they do again. He told me he is going to Solapur. कुछ नहीं, खाली अपना ही. हाँ. And we'll take some feedback. हाँ, group photo. वो photographer उसको बताना पड़ेगा. What about magmatites? Exactly. What about magmatites? So first, if you have to date a magmatite, what are you dating? No, that we will not call partial melting, exactly. So when it comes to migmatite, the process is migmatization. Okay, so what are you dating? You are dating basically anatexis. Okay, so the process is not partial melting, the process is anatexis. But a migmatite, a gneiss for example, which is converting into a migmatite, may contain still biotite. What you have to ascertain whether the biotite that you are sending for your dating or your isotope characterization, whether it is affected by the process of migmatization or not affected. So you can have biotites that can be zoned, or you can have biotites that have reactions, metamorphism. See, there is no substitute for the humble. Still, you can do geology with a strong will, with a hammer, with good lungs, common sense, and with a Brunton. Right? And we are very lucky in our university. We have the tradition of publishing papers that are based on these, not on machines. Okay. So what we are trying to say, because we are petrologists, and that's exactly the difference between, and that's why we are having these lecture series together. We have a person who is in the lab, who is an expert in the lab. He has tremendous, you've seen the precision and the accuracy on the analysis, right? It's not very easy. Malika will discover that, okay, when she grows fatter and older. क्योंकि तुम लैब में रहोगे, तुम बाहर जाओगी नहीं. हाँ, you will have a hamburger in the lab because there is no time to go and eat. बराबर है ना? ऐसा ही है ना? है ना? Satyanarayan sir is not becoming fat because he is having tension. Okay? Otherwise, all lab people are like that. So do you get it? So what you put in, you have to learn the subject first and then apply the isotope to it. Okay? So you have many answers. For one or two answers that you don't know, you will apply isotope geochemistry. And at the end of it all, you know that the isotope geochemistry has also not helped to answer those questions. Then you have to hang up your boots and say, okay, I tried. That's it. Okay, someone else younger and with better sophisticated instruments and better ideas will probably answer that. Not everything can be answered in your lifetime. You should not attempt it also. Right? So the process becomes very important. So what I was saying is that we are having a classical petrologist who has modern ICP-MS connotations in terms of Michel, with a geologist who is running a stable isotope facility. He is not a physicist. Right? In other labs, we have physicists. They do not understand the process. And yesterday, they were saying this. Many physical laboratories have physics people running earth science samples. You have to understand the biotite. If you do not understand the biotite, you do not understand the number. You have to understand the calcite. You have to understand that calcite is the dustbin of all trace elements. So any enrichment is not surprising. But if there is an enrichment, yeah, because the structure is so well. If there is an enrichment, it has a number that is significant. So you have to think mineralogy, you have to think petrology, you have to think geodynamics, because every geodynamic, every time a rock is folded, it's the mineral that is accompanying the folding. I hope you understand this. Lineation and foliations are developed by minerals. So they open or close. The latest that we heard for carbonatites was a good work by Anton from Anton Chakmordian, where he said that shear zones, subsequent shear zones in carbonatites enriched Re. Why? Because the frictional and the deformation accumulated Re is in the calcite. So if you have by mistake you have sampled a carbonatite or a calcite from a shear zone it will behave differently than the normal calcite in a marble. So still very, very preliminary information is to be generated like that. It comes as a surprise. It comes as a surprise, and he has beautiful maps of those calcites where the diffusibility of RE is increased because it opens the system up. It opens the calcite. It's not closed. So in shear zones, you have the RE mineralization. Of the shear zones, there is no RE mineralization. And that makes economic sense because shear zones are open and they can be fluid flow in that, or even simple mechanical disintegration. You can just dredge the shear zone and you have all of the RE. Or you can develop a method and patent it, of course, for beneficiation. Can you artificially create shear zones and accumulate your RE? Like what they do for uranium, they do heap leaching, no? They do heap leaching. So can we do something like that? Why? Because we understood the calcite accumulates the RE. So therefore, there is no substitute for these fundamental works, right, of petrography and preliminary geochemistry before you go on to isotope. Okay, so it's just a preliminary talk that we are thinking. I know the seniors are already knowing this. The juniors have to know this. I am just trying to stitch it between it. So I'm not going very deep into it and not going very superficial into it. Right? So these are the aspects. Yeah. What is? Batch melting. In terms of what? Okay. So this is a general concept, batch melting. Okay, and I may sound very controversial on tape, but let me say it. Right? So again I say that because we are taught magmatism in the same class from the same textbook, and therefore we tend to mix processes, right? Like just now we said assimilation, he said partial melting, but it's actually assimilation, the process. Like that you are saying batch melting. So batch melting in terms of felsic magmatism will have totally different connotations than batch melting in, say, mafic volcanisms. But what happens is that it is spoken and stitched together in a class together, right? So in case of batch melting, if it is mafic, for example, if it is mafic, I will impose to what he said in terms of partial melting. If you remember the diagram, in Michel's presentation, this was the diagram that these are CPX, for example, and a lot of material like that, or say garnet also. And this could be a classical example of partial melting, right? That means only the edges of these minerals go into the melt, right? So this becomes evidence for a partial melting. So this is partial melting 1, right, in terms of mapping. So peridotite is undergoing partial melting. Now, how does the partial melting occur? The partial melting occurs by adiabatic. That's the question. One of the questions in your paper. By stretching of the lithosphere and by adiabatic decompression. So when you decompress, it's like a pressure cooker. Always I give the example. The seniors may be fed up of it. Right? And when you cook rice, after you put the gas off, when you remove the lid or you remove the whistle, there will be still some boiling going on. Right? So that's decompressional. Something like that, decompressional melting. So the more you lift, the more you decompressional melting you get. So the partial melting over here for time 1 is this. So that's one batch of melting. For T2, you will still have partial melting, right? That will be T2. Right? So because of buoyancy, the PM1 has gone up. The PM2 is here. The PM3 is here. So these goes on in batch melting. So in mafic paradigm, this is batch melting. For granites, it will be totally different. For granites, batch melting will be totally different. But since we are doing mantle petrology, I thought I will say. So what it is, every time you decompress, you create a batch of partial melting. Every time the batch migrates, because newer and newer. So what will happen over here is you convert this into a rest type. Okay. So what Matthew was saying is that in his whole life he's seen that 20 meters thick lava flow on Kilimanjaro, and he was impressed until yesterday when he went to Mahabaleshwar and he said, see the kilometers of lava. Right? So if you have a kilometer of lava, think about the amount of partial melting that has happened. So what will be remaining in the mantle, upper mantle down there, will be a refractive, non-reacting residue. And that residue should be what? It should be dunite. Okay? But what happens, and that is not reacting, is called the subcontinental lithosphere, SCL. So beneath the Deccan, there are many people who ask this question, what lies beneath the Deccan? At 40 kilometers, you know that it's going to be a depleted mantle full of dunite. Okay? And that is what needs to be understood by geophysicists. Apparent resistivity, model कितना use करना चाहिए? Whether it should be a pyroxenite, whether it should be a dunite, or whether it should be a husbandite. That's exactly what Michel, and probably because of the accent you are not catching what he's saying. But for the geophysical modeling, this comes into play. Right? So below the Deccan, with 40 to 60% of partial melting, because the lavas have to be produced that much, they are not melting in the garnet stability field. They are melting in the spinel stability field, so they will be shallow. And then, of course, how much is crustally contaminated. So in the Deccan, you will get an array, isotopic array. An isotopic array, for example, like this, where there is an epsilon UV function. You should get anything like this. Right? But that's the continental crust. That's the continental crust 2. Okay? And that's the uncontaminated lava. Nothing above, nothing over here. That's the lava pattern that you will predict. But for a geophysicist, what will happen? So what will happen there? For a geophysicist, you will get lavas like this. One layer. So how many layers model this is? One layer model this is of the entire lava pile. Then you will have continental crust. Right? And now if you see in all of the geophysical models, they put this. Here they do not know whether they can. Therefore they model it for 3.9, isn't it? They model it for 3.9. But we know that the dunites and the lertholites and this thing will have difference. Right? And so it's not their problem. It's that good geologists are not telling the geophysicist what to model. Right? So what needs to be done is that this entire mantle then needs to be broken down into the major parts of dunite and husbandite.
And if there is magmatic underplating, then you will have series of pyroxenite, or you will have series of. So what you learn on the mid-oceanic ridge, or what you learn in the ultramafic massif, then translates to the subcontinental lithospheric. And that is why these studies are very important. Why? Because seismic tomography. Some of the seniors were there when Sham Reiser produced his Magma-mantle map. Okay, and he said no, the petrologists have to tell you what to do. Right? And that's the paradigm. The petrologists now have to tell him, because he's got this whole domain at 40 kilometers. This domain is not a single domain. So I have to tell him whether it's a 3-phase domain or whether it's a 2-phase domain. And that's how the modeling will be. He is blind. He cannot tell you anything about it beyond that. Right? So it starts from petrology, goes to the geophysicist. Geophysicist is blind on one side, cannot do anything beyond that. Okay? And then there has to be subordinate studies by the petrologist to come back, and then there is a review. Until that happens, we are still going to be followers in science. Right? Someone from Caltech will do this. Right? And geophysicist and petrologist, as you see, geochemist and petrologist cannot see eye to eye. So it's time that we understand each other's problems and prepare better models. Right? For example, 3D seismic model. This is very important. So every time you find a xenolith, every time you find a fragment of the lower crust, granulite and eclogite, you must be able to do the petrophysics of that. And until we do the petrophysics, we will not go to what Michel is saying, or what Sue and Bill were saying 3 centuries back, 4D lithospheric mantle. And if we can't do 4D lithospheric mantle, we will not be able to tell where significant mineralizations are. Right? So this idea, Bhaskar sir and Babu, they were doing it from the kimberlites, and we were trying to do it with the eclogites in the basement. Okay? But the dots are far few, so there should be many students who come in and do this sort of work. It's the numbers that matter. Right? And therefore, in that endeavor, we are having these training programs so that it is handed over to the next generation altogether. Right? And this is what I wanted to say. The papers have come, so we have consumed time nicely. Okay. Tomorrow we will do some other topics. So first, mantle petrology.
The ones that are already prepared, that's it. No. No, we can have a discussion on that. They are not going to.
हॅलो हॅलो ह्याचा कॉर्डलेसचा प्रॉब्लेम नाही ना कळेल तो हेलो 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 है तो ना